First of all, many thanks to the organizers for organizing this event here in a very nice place with very nice topics, and also for their support that I can participate in this event. I will talk about the joint work with Lorenzo Diaz and Michael Rams and a few others, but I'm not talking about all the extensions of these works we have been doing. I will talk about today an aspect of a multifractal analysis for Lyapunov exponents, and I will concentrate on essentially on matrix products. So I would like to first state some classical results on matrix cocycles. So suppose that you have two matrices A1, A2 in SL2R, SLDR, in fact. And first I would like to define the Lyapunov exponent for concatenation of those matrix cocycles. So if you take a sequence and some number and define this concatenation according to your sequence. And so defining all these possible concatenations, that would define you a semigroup generated by this family of matrices. And I will put some natural assumptions. I will assume in the beginning that the cocycle is strongly irreducible. This means that there does not exist a finite family of subspaces such that the subspaces, their union is invariant under the semigroup. So invariant under any element which you obtain by concatenating these matrices. And second condition I will put is proximality, meaning that there is some concatenation such that the matrix has real eigenvalues with different absolute values. Okay. Then it is well known, and there are several ways to stating these type of hypotheses. I will just focus on a special case. And references mostly go back to Fürstenberg from '63 that says that if you take a Bernoulli measure with the probability applying on these two matrices, non-degenerated, then almost every concatenation gives you that the limit of the norm as n tends to infinity. First, this limit exists almost everywhere. This is, well, nowadays just Kingman's ergodic theorem, but at the time Fürstenberg and Kesten were perhaps the first to phrase this. So this limit exists. It is equal to a constant depending on the probability vector, and that's for me important at that point, it is positive. Okay? So regardless of whatever Bernoulli vector you take. And this is sometimes called the top Lyapunov exponent. of the co-cycle and of the Bernoulli measure. Okay, so there are immediate counterexamples that show you that the hypotheses I put are indeed necessary. So for example, if you take a hyperbolic matrix, lambda a number bigger than 1, and a rotation by pi over 2, so this matrix has two eigenspaces, and the rotation just swaps the eigenspaces, and then if you take any Bernoulli probability non-degenerate, this will always give you a positive Lyapunov exponent, zero Lyapunov exponent. And this example is not strongly irreducible. And as I said, it for any vector non-degenerate. And the second example, if you just take two rotations, then, well, rotations immediately also get zero top Lyapunov exponent regardless of whatever distribution you take, in particular if you take a Bernoulli measure. Okay, so, and this map is not proximal. Okay, so these are the classical results by Fürstenberg. In my talk, I will try to explore the, do multifractal analysis on those type of Lyapunov exponents, looking at a slightly more general setting of skew products. I will explain this in a minute, and I will also explore on how far I could play around with this condition of Bernoulli distributions to get positive Lyapunov exponent. Okay, so for that I will concentrate on SL2R. Well, I will only talk about, not concentrate, only talk about SL2R co-cycles. So there are a number of questions you can ask. First, so if you start with a bunch of matrices, well, it doesn't need to be just two matrices. Take any finite number. You could ask what is the range? What range of top Lyapunov exponents? Well, as I said already, the existence of this limit of almost every sequence does not depend on the Bernoulli measure. You take any ergodic measure in the shift space, and you get a well-defined Lyapunov exponent. So, and then you could ask, what's the range of values? So, minimal and maximal Lyapunov exponents, in particular, when is this equal to 0, the minimal value? Of course, they're non-negative. And as I said, one challenging question is how far you could weaken the Bernoulli hypothesis. And so Bernoulli means that you look at an IID random matrix products, and there are some extensions of these hypotheses. One of them is more recent. There's Wirtzer from the 70s and Goldscheid from 22 that looked at stationary and non-stationary Markov chains and have the same type of results. So for any stationary or non-stationary Markov chain of matrix products, you get non-zero Lyapunov exponent. So in general, you could ask, if you look at the shift on the sequence space, the left shift, and take a measure which is ergodic, not necessarily the Bernoulli measure, well, you define the type Lyapunov exponent with respect to nu, and would like to ask the following multifractal questions. So if you look at, given an alpha, well, and a measure whose exponent is equal to alpha, which is, so in my talk, unless I emphasize this, measures will always be ergodic. So you look at the entropy of this measure and take the maximal value. So this is defining your function. And you would like to express the, well, describe this function. And so this is in terms of, I will call this E of alpha, E for entropy. And you can see this as a restricted variational principle for entropies conditioned on those measures which have the given exponent alpha. So this is the ergodic point of view of the multifractal analysis of those Lyapunov exponents. And the second point of view is, again, given alpha, you look at the set of sequences such that, well, here you may define this as the Lyapunov exponent of that sequence, provided that the limit exists. So you would ask for those sequences that have this Lyapunov exponents, a kind of level set, and you would like to see what is the size of this person. And here I will look at the entropy of my shift on the dynamics of I'm studying on this level set and ask about the description, regularity, whatever. When I am on the shift, so if you don't recall the definition of topological entropy of, well, these are invariant, but in general not non-compact, so quite complicated fractal sets, then just think of the Hausdorff dimension on the shift space. Okay, so these are relevant questions. Moreover, I would like to see, describe, provided that I do get some sequences, perhaps I need to change my hypothesis, that this set is non-empty, that there are sequences that get zero Lyapunov exponents or ergodic measures, not Bernoulli, under those hypotheses that realize the exponent alpha, then I would like to describe this value. Okay, so these are my some relevant questions which I like to answer. Okay, moreover, and this is work in progress, for those values I would like to describe those measures. They're not Bernoulli, but what is the complexity of those ergodic measures? Okay, so our approach is to go away from the matrix co-cycles and to look at skew products. Okay, this is for mainly two reasons, or three reasons. Matrix, first of all, matrix co-cycles are very special cases of skew products we are studying. Well, I will say this in a minute. Second, they provide us the technical tools to deal with this multifractal analysis. So they give us the tools. And thirdly, they are a playground for understanding non-uniformly or partial hyperbolic diffeomorphisms, but I'm not talking about this. But they provide some toy models which you can try to understand and then try to generalize and get some idea what could be true in a more general setting. Okay, so instead of looking at the matrix co-cycles and the action of the matrices, I would like to pass to the projective action. So given a matrix, I will define its projective action. And if I start with a finite collection of matrices, I will end up with very special circle diffeomorphisms. I will interpret the action on the projective lines and understand those maps as very special C1 diffeomorphisms on the circle. Okay, and given this, I look at the skew product. I don't need to. Look. I can use my own force. It's good. Okay, I hope I didn't break anything. Okay. Huh? No. Okay, so I look at the following map. The first coordinate, the shift on my favorite shift space, and then the circle, which maps. So this is a point on the circle. As I said, the shift in the first coordinate, and in the second coordinate, I just take the corresponding map, which is determined by the first coordinate in the sequence space. Okay, so this gives me a skew product, in fact, a step skew product. As they depend only on one coordinate, are piecewise constant. Okay, so well, my initial question was about the top Lyapunov exponent of those projective action. How does this translate to the skew product? Well, as I said, there are very special diffeomorphisms, so I can look at the associated fiber-Lyapunov exponent. So if I take a point in my space, which now has two coordinates, then I can take the concatenation of those fiber maps, as I did before. Here I concatenated the matrices, and now I concatenate the corresponding diffeomorphisms. I differentiate, and I look at the growth as n goes to infinity, provided this limit exists. And in this case, I will call this xi of xi x. Okay, so this would be my Lyapunov exponent at that point. And if I have a measure mu, which is an ergodic measure for my skew product, then for almost every point, this exponent exists, and in fact depends only on the measure, and is the integral of, well, you can take the logarithm of this concatenation and write this as a Birkhoff sum, and this is nothing but the integral of these numbers. Okay? So you notice already that here I was dealing with Kingman, so here I had the subadditive sequence behind to guarantee the limit, and now I am in an additive setting. Well, this is not yet the big advantage, but sometimes it helps.
So when do you know that the limit exists? Because you don't have any subadditivity.
No, it's additive. In this case, it's just additive. The log of the, I mean, it's one-dimensional.
All right. So the limit is, I mean, it doesn't always exist.
No, it's not. Of course not. If it exists,
So when do you know that it exists?
if the measure is ergodic, it's just Birkhoff. No? So if it exists, then I can talk about this number. Okay, I can move this. Provided limit exists. And I would only like to call this an exponent if the limit exists, otherwise you can look at lim sup, lim inf, whatever.
Excuse me, what is the sine u?
Is that? Say it again?
What is the sine u?
So psi of mu you could define as the integral what comes out of the Birkhoff theorem, and this is then an equality because of ergodicity, right? Chi. I don't want to use lambda for exponent, I don't know, chi. Okay, so you have this Lyapunov exponents for the skew product, and because you are, I mean, I'm focusing on my talk on the matrix co-cycles, but however, this step skew product you can consider on its own. But I will, and so you just need to assume that those are differentiable maps and perhaps some integrability condition. So if you assume that you have a family of diffeomorphisms, C1 diffeomorphisms, then you're fine. Okay, so, but in the case of the matrix co-cycles, and the derived C1 circle diffeomorphisms, there is a dictionary so if you have a measure mu which is ergodic for the shift map, and assume that you know that its Lyapunov exponent is different from 0. So for example, if nu is a Bernoulli measure, then you know that there exist two measures. Sometimes they are called twin measures. When you deal with skew products, you have some dynamics in the base, and then you look at the corresponding dynamics in the product that projects to the objects in the base. So there exist two measures which are ergodic for F. And there's a relation for their Lyapunov exponents. So the Lyapunov exponent of these ergodic measures for the skew product are twice their absolute values are twice the top Lyapunov exponent of the measure in the base. Okay. Well, there are a few other results. For example, about fibers where those exponents are not existing, you can derive some relations. I don't want to talk about all of them, but just to mention one more. So if you have an ergodic measure with zero Lyapunov exponent, then for new almost every fiber and for all points in the circle, these Lyapunov exponents are equal to 0. So you get, on the sense of on the level of measures, measure in the base, you get measures in the fibers, Lyapunov exponents in the defined on the base, you get Lyapunov exponents in the fibers. Okay. Okay. And perhaps one more. If you have a measure in the base, and you look at, so let me write some more. Well, I'm not putting a very, well, here, okay. Here I denoted the entropy of that dynamics on that set. Here I wrote only the entropy of the measure. So if I have a measure, maybe for people that prefer to be always very precise in noting all the dynamics in the, putting the dynamics in the notation, so that I would like to have the metric entropy of the measure in the base relative to the shift. And because I have a one-dimensional fiber, I know that there is some relation between the entropies, between the one in the base and the one in the product. So if I look at the projection to the first coordinate, then I see always the same entropy. So there is no entropy in the fibers. The entropy of any measure coincides with the entropy of its projection. Okay, so okay. Oh no, there's not yet. Okay, so I have my questions. Now let me say something before stating a result. Let me put some hypotheses. I don't want to continue living just with these strongly irreducible and proximal. Perhaps it's also, well, it's not sufficient. So I will assume that the matrices are time is running very fast, so I may not be able to talk about the full hypothesis I'm putting. So let me just say that they are generic elliptic with some hyperbolicity. So what means elliptic? So matrices are classified by trace. So if I have a matrix A, and its trace in absolute value is bigger than 2, then A is hyperbolic. Smaller than 2 is elliptic. And there are also parabolic ones, which I don't need for for right now. So a hyperbolic matrix is, well, there's one over there, and its action, projective action, has 2 fixed points and looks more or less like a North Pole, South Pole map. And an elliptic, a rotation is an example for an elliptic. So rotation would give me an elliptic matrix. There is a so-called hyperbolic co-cycles, which assumes that there exists a cone field which is invariant under the entire semigroup. So, which is invariant on all matrices which you get by concatenation. So this is the hyperbolic co-cycles. And then by definition there are all the elliptic ones. So this is then a subset of SL. Let me focus on 2R. If I fix a number of matrices, if you want, you could put here and that one. Okay, so elliptic co-cycle is the one such that there exists a matrix obtained by concatenations which is elliptic. So these are the hyperbolic and elliptic co-cycles, and there is a result by Yokos and Avila Bocchi-Yokos that such that saying that the union of those two classes is open and dense. Usually people study only the hyperbolic ones when studying Lyapunov exponents. Those people also prove that the closure of the elliptic ones is the complement of the hyperbolic ones. And the class of generic elliptic with hyperbolic, they are inside that we are going to study, there we have been studying, are inside in the elliptic ones. And we show that there exists a set in the elliptic ones with some hyperbolicity, which is open and dense in the elliptic one. So we are really inside the elliptic co-cycle. So let me just give a sketch of the hypothesis, and if there's time, I can say something more specific at the end.
Sorry, you said E itself open.
Sorry. The union is open and dense in the set of all co-cycles.
Yeah, but do you know that if E is open?
Yes, but not necessarily dense.
Okay.
Yeah. Okay. The union is open and dense in the set of co-cycles. In fact, they have a very nice characterization of the boundary between. It's very, very, very nice topic to study. Okay, so we look at some set which, roughly speaking, has the same structure. So if you have a hyperbolic matrix, and as I said, it has a fixed points, an attracting one, and a repelling one, and you could like fix some interval and some interval, and the hyperbolic matrix comes with a cone field, say, that maps this cone strictly inside itself. And the same thing for some cone and the inverse map. And so you assume, so I'm not trying to give an idea of the hypothesis that I put on this class. So assume that there is some H of this type in your co-cycle, which comes with these absorbing intervals I and j. And then you also assume that there exists some m, some integer, such that for any point, well, or point or vector, depending on which point of view you are, such that for any point there exist sequences xi and eta, and there exist numbers s and r bounded by m, not depending on the point, such that, let me just make a picture. So if you take any point x, there is some iteration by at most s iterates of some sequence into that absorbing interval. And so, okay, let me write this such that f and the same backwards. Okay, so concatenation of the diffeomorphisms F, which are induced by your matrices in the cocycle, and then you assume the same for the maps or the inverses of those diffeomorphisms. So again, you have some hyperbolicity and then kind of minimality. From any point in a bounded number of times, you can get into that absorbing set. Okay, so the origin comes from a more general analysis for C1 diffeomorphisms, but let me just keep it at that point. Okay, so as I said, we want to understand what are our questions. We would like to understand the range of Lyapunov exponents and this restricted variation in principle for these top Lyapunov exponents. And as I said, I can translate this to the Lyapunov exponents of this skew product. So we are always standing on the shoulders of others. So there are some papers by Bocchi, Bonatti, Diaz, Rams, Kwietniak, some others that say that in this setting, this E of 0, well, first there are measures which are giving zero Lyapunov exponents under those hypotheses, and in particular, there are measures with positive entropy that give zero Lyapunov exponents. So they use blenders and flip-flops. This is techniques from partial hyperbolic theory I'm not going to talk about, but they prove already that this is a positive number. There are also some classical results which you might recall the Bowen's paper from 73, which holds in quite general terms, that tells you if you look at the entropy of some homeomorphism on some set, then this is always bounded from below by the supremum of the entropies, which are invariant, which are seen this set. So, and here, as I said, measures are always ergodic, unless I'm saying something else. Okay, so if you take this result, then you could already guess that this number that I defined there is a lower bound of this entropy, where this is the set of points for this Q product such that this fiber-Lyapunov exponent is equal to alpha. Okay, so moreover, this results by, for example, Pfister and Sullivan and Fan, Liao, and Perrier, that says that if you have a specification compact invariant set such that the dynamics satisfies specification, then E of alpha is equal to the entropy. Moreover, here not necessarily you need to look at ergodic measures, but you can take any measures supported on this set gamma. So you take the restricted variational principle on this subdynamics. Okay. So okay. Now let me state a theorem. Okay, I do have space. Let me see if yes, okay. I forgot the shoulders of the others. That there exist measures. There is one paper by Klepsin, Iyashenko, Gorodetsky, and Harsky, which gives you, well, they are working in a slightly different setting, but almost comparable setting of skew products. But when I say setting, is the topological hypotheses on the fiber maps are slightly different, but they guarantee that there exist measures such that there are fiber-Lyapunov exponents. Okay, so theorem is the following, assuming that I have a cocycle which is elliptic with some hyperbolicity. Let alpha min and alpha max be the maximal and minimal Lyapunov exponents. Then the entropy, let me recall the definition, the supremum of measures, the entropy of measures such that the top Lyapunov exponent is alpha, new ergodic. Okay, well, this was the definition. This is equal to the entropy on this Lyapunov exponent on this level set. It is equal to the entropy of the level set in the base. Yes. Sorry, I just noticed that time is running too fast, so that's okay. So these two numbers coincide, and they can be equivalently described as this number. So, and this here is nothing but okay, so this is equal to, let me put this, let me write this in colors. If alpha is positive, if alpha is negative. So this is the Legendre transform of some pressure. Okay, and okay, of some pressure function. I will say a bit more in a minute. Moreover, E of 0 is positive. Well, as I said already, this is, you could deduce this from these results, but we give an independent proof. And smaller than the entropy of the full dynamics, which is log n, in the case this was generated by n maps. Okay, so this is the result. And maybe I have some more minutes to, oh no, okay, one more addition. So, standing on the shoulders of this construction by Klepsin, Ilyashenko, Gorodetsky, and Nalsky, and Kwietniak and Wonska, who proved that, well, okay, maybe I say something later, you get a characterization for the measures that give you, for some of the measures that give you 0 exponent. So for any epsilon, there is some set of ergodic measures in the shift space, which is path connected, such that for any measure in this set, the Lyapunov exponent is 0, okay? And this measure is loosely Bernoulli. Loosely Bernoulli is generalizing the very weak Bernoulli property, and it says that it is Kakutani equivalent to Bernoulli isomorphisms, but maybe I don't have time to say something more. Oh, you see? So these are the two statements. So you get the formula for the for the multifractal analysis of those Lyapunov exponents in terms of restricted variational principles. So let me say something about the proof, some ideas. Okay, so if you go back to the example I have over there, I have a hyperbolic matrix and a rotation. So if I take one map F1, which has, for example, coming from such a matrix, then I get here a repeller and an attractor, and the measure which is obtained by the Dirac, for example, just applying this map and sitting as a Dirac measure on my repeller. So if I call this mu1, this is a hyperbolic measure in the sense that its Lyapunov exponent is just the fiber derivative of this map in this repelling fixed point, so it's positive. Okay, now I can do the same thing in the attractor, just change here, and I get another measure which has negative Lyapunov exponents. And then when I have supposedly one rotation, say by some map F2, then the measure that repeats this fiber and sits, well, for example, you can just take the Lebesgue measure. Then this is okay, this is 1, 2, 1 or 2, 1, 2. Then this has Lyapunov exponent 0. Yes? No? Okay. So I get 3 types of measures. So I take my space of ergodic measures for the skew product, and it splits into ergodic measures which have a negative exponent. I have my ergodic measures which have positive exponent, and I have my ergodic measures which have fiber-Lyapunov exponent. Okay, and okay, and I do the analysis separately in. So I split my measure space in these 3 types of measures. In this case, the repeller times, so if I take here the sequence in the base times my repeller, this is a very special set which is compact and F-invariant. Okay, so it's a compact F-invariant set which is fiber-wise expanding. Now I can generalize this to more general sets that I get, in fact, well, this is a measure which is sitting on a fixed point, so it has 0 entropy, but you can, your system has positive entropies, so you find positive entropy in F ergodic measures, so you get, in fact, horseshoes. So you get, there exist horseshoes, F-invariant compact sets with some very special properties. In particular, they have the property that I mentioned here. It was somewhere, the specification property, where it was. Specification, here, okay, gamma. Okay, so particularly I have the specification property. Okay, so you can stand on the shoulders of the others, restrict to those hyperbolic sets, do the multifractal analysis there. So you have your range of values for alpha. And if I take a horseshoe of that, I get a range of minimal and maximal Lyapunov exponent on this compact invariant set. And I can look at, let me write this here. So I would look at the measures of, so they are F invariant, but supported on these horseshoes and the ergodic, and look at this restricted entropy function, and the theory tells you that this is equal to the entropy of F on gamma on this set. Okay? And moreover, it tells you that it is a Legendre-Frenchel transform of some nice convex differentiable function, which is given by the pressure on this set. So it is something like this. Okay, so this you do on good horseshoes inside, and given any, and then you do an approximation step, roughly saying that if you have any value, you can arbitrarily well approximate by horseshoes that contain this value. And all these sets sit inside your product space, so you get an increasing function of curves. Well, in fact, they are not defined this way, but they are defined as Legendre differential transforms of the restricted pressure. And here I said restricted because they're precisely restricted to the set of ergodic measures with this Lyapunov exponent. And this defines you a convex, hence continuous function, the pressure, and its Legendre transform is also a continuous concave function and attains its maximum at the entropy, has on some domain. It contains the zero value as smallest value, for example, using those results that guarantee that there are such measures. And analyzing the properties of the pressure functions, you show that, and of the Legendre differential transform of those pressure functions, you show that this value is strictly, well, it's already positive, this, for example, can deduce, but it's also less than the maximal entropy in the system. Okay. Maybe this is, okay, perhaps open questions. There are lots of there are more questions than answers in this topic. So I only talked about the case of matrix cocycles and then used fiber-Lyapunov exponents. So as I said, for the definition and all these and in fact for the results, you just need to assume that you have a skew product with C1 circle diffeomorphisms, which satisfy some hypotheses, which are more or less hidden in these hypotheses for the matrix cocycles. But already in the case of matrix cocycles, so you know that this function is nice and differentiable on this part. You know that this value is positive, so this is the supremum of entropies with your top Lyapunov exponent, ergodic measures. But even, for example, you don't know if this value is achieved by some ergodic measure, if it is unique or not, if you have examples, counterexamples. And well, what this second theorem says that you get an entire interval of measures which are of that type and which are loosely Bernoulli, and somehow show you how far you can go beyond the Fürstenberg result on the Bernoulli IID or Markov chains to understand the ergodic nature of those measures which realize. But I think I stop here. Okay.
Good. Question or comments?
Is there a reason why you excluded the parabolic case from your considerations?
Say it again?
Is there a reason why you excluded the parabolic case?
No. Well, it's not important for the definition, so I was in a rush, so I skipped it. So trace equal to 2 is the parabolic case, but it's not used for the definition of the class.